This video is for sections 9.3 and 9.4, all about regression. So let's dive in. So the coefficient of determination, usually denoted capital R squared, measures the proportion of total variation in the response variable that is explained by the least squares regression line. The coefficient of determination is a number between 0 and 1, including 0 and including 1. So in mathematical language, you would see it written as such. If the coefficient of determination is equal to 0, the line has no explanatory value. If r squared is equal to 1, it means that the line explains 100% of the variation in the response variable. So if you were thinking about this in terms of coefficient of correlation coefficient, then there would be a coefficient of determination of 1 when the correlation coefficient is also 1, meaning all of the points are lined up directly on the line. So if we were to predict any values, it is very likely those values would fall directly on the line. And as the coefficient of determination is closer to 0, then we'd have a lot more spread in the data, and therefore the predicted values would have a much larger error margin. So computing and interpreting the coefficient of determination, we're going to run through this example in the PowerPoint, and then we're going to switch over to RGuru so I can show you how you would have done this in an RGuru type setting. These data sets I've already transformed into Excel files and placed them into the Blackboard shell, so you can download them from there, which you will have to do first before you are able to upload them into our statistical software, RGuru. So the data to the right is based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins is the predictor variable, or the x, and the time in minutes to drill 5 feet is the response variable. And here is the data. So if we begin at 35 feet, then the next 5 feet to drill took 5 minutes and 5.88 minutes. If we started at a depth of 175 feet, to drill the next 5 feet took a little longer, 7.62 minutes. So just by looking at those two data points, it seems as though the deeper we are to start, the next 5 feet in drilling will take longer. Okay, if we graphed a scatter plot of depth in comparison to time, we can see that we are creating what looks like a positively sloped line, but there is quite a variation between the points. They are not so tightly knit together. So we get at a correlation coefficient of maybe 0.7 is my guess anyway. We'll calculate that exactly when we throw it into RGuru. So if we calculated the mean depth that was used in this data set is 126 feet. The mean time was 6.99 minutes. And standard deviation, if you recall from Stats 1, our standard deviation helps us understand the spread of the data. So the correlation between depth and time is 0.773. I actually did not look ahead. I don't remember what it was saying. So that was a really good guesstimate on my part. We knew it was positive because it was creating a positive line, and I didn't say anything close to 0.9 because the dots were so spread apart, but they still were forming a pretty clear line. Regression analysis. So if we take a look at the regression equation, you would have your intercept plus the slope of the line times the input depth gives us the time. So suppose we were asked to predict the time to drill an additional 5 feet, but we did not know the current depth of the drill. What would be our best guess? So our best guess would be 6.99 minutes, because that was the average or the mean drill time for the additional 5 feet. So without knowing exactly how deep we are starting, we would guesstimate the average. But if we did know where we started, say, for example, we are starting at 160 feet and we wanted to predict the next 5 feet, let's say 160 was not part of the data set, we would take our regression line, we would throw 160 in the input and calculate, and we would then estimate that it takes 7.39 minutes to drill the next 5 feet at a starting depth of 160 feet. Let's now jump over to our guru so I can show you how to gather all the information that was in the PowerPoint from our statistical software that we're using. One moment for me to grab the right screen to share with you. Here we go. Okay, so I've already logged into my account. So we are going to head over here. Remember, you have to download the Excel files that I posted in our class before doing this part. It has to be on your computer somewhere. And we're going to import the drilling data. So I'm going to go to Data, Data Import, Import Dataset. Choose. I put it. Oh, well, actually, I don't have to do this part. So you would choose a file and hit upload. I already have it uploaded in here. That's why I didn't save it anywhere easy. So then again, when you put in any data set, make sure you double click it. That's the wrong set. Make sure you double click it in your data list to make sure it imported correctly. I did already fix it in the Excel file so that, ooh, that doesn't look good. That doesn't look right. So maybe that's not the correct file. Let me see if I have it in here again. Maybe it is because I just played with this and I thought that was the right file. Let me just double check that I'm using the right file because those NA values are strange. I feel like that's from a messed up version. Example, no, we're not 10.3, we're 9.3. This is our next example, but not there yet. Okay. I don't particularly like what this looks like, but I guess let's see if we can get the right numbers. If not, I'll have to re-upload a different file. Okay, the NAs are concerning, but let's see how it looks. So we're going to go to plot and scatter plot. Let's see if we can get the same scatter plot that we saw in the PowerPoint. We are going to use our drilling data, and our predictor is the depth, and the time for the next 5 feet is the response. I want to see the least squares line. I want it to show me the correlation in the least squares equation to save me some time. I should probably title my scatter plot. So this will be drilling data. My x-axis is the depth, and my y-axis is the time. So if you're handing this in for any particular assignment or project, make sure you have labels for your title and your axes. So we did this part last time. So here we are. This data looks great. It looks just like what it was in the PowerPoint with our regression line. And as we continue through this video, I am going to explain to you what it means for these dots to be off the predictor line and what does that tell us. So our correlation coefficient is R equals 0.77, which is what we knew. If we wanted to calculate the coefficient of determination, all we do is take that number and square it. There is an analytical way in our guru to get that value, which I'll show you in the next example. Here is our regression equation. So 5.5 plus your slope times the depth, which we would use to predict any given input that we want. Now, if we wanted to get that summary where the mean and the standard deviation was given, so then we would go to summary statistic. So I went back up to data and over to functions, and to get a basic summary where you get the quartiles, the mean, the median, you can do a range and an IQR if you want. I just want to see standard deviation. So I'll select my drilling data, and I will select depth for the X variable and time for the Y variable. And let's see our, you know what? What's my error? Nothing has changed. Do you want to continue? Wait, let's preview anyway. Okay, so it's apparently having it's not working today. I will figure out why it's not working, but that's how we would get our mean and our median and all of that good stuff, is by using that, because I don't think there's one under the analysis for just some basic summary. No, it's under the data. So let me try it one more time, but maybe I should leave the other ones blank. So if I go back to summary statistic, select my drilling data, so we are problem solving on the fly. This is start off, so I know that we need to have a variable selected for the starred ones. So let's see. I think this will just give us, okay, so this gives us the average drill. Okay, so here we go. This gives us the average drilling depth, which it corresponds with what we saw in the PowerPoint, and then all of the other values that we might have. So maybe I also want to see the summary statistics for the time. So I would select the same data set, but select time for this factor. And I have the average time, which rounds to 6.99. So that's how we can get our average really quickly, our 5-number summary, our standard deviation. If we wanted variance, there was a selection box for variance as well. Let's head back to the PowerPoint now, so we can talk about some other things that are really important. Okay. So let's talk about those differences between the points and the predictor line. So the difference between the observed value of the response variable and the mean, that 6.99, or actually the 121, because it's the response variable, so it's the depth mean, is called the total deviation. I'm going to show you a picture, so if that makes no sense, don't worry, I'll show you a graphic. The difference between the predicted value, which would be the value on the least squares regression line, and the mean value of the response variable, the mean depth of drilling, is called the explained deviation. It means that the variation between the y values that can be explained by how the initial depth time would be explained by this value of the predictor line and the average line. And what is the difference? Again, I'll show you a picture, because these definitions without the pictures are even harder to explain. So the difference between the observed value of the response variable and the predicted value is called the unexplained. Let's take a look at the picture now, so that I can go over these again. Okay, so here is your predicting line. This is your average depth, starting depth. And we are saying that the difference between the actual observation value, the dot that's not necessarily on the predictor line, and the average response is called the total deviation. How far in total do they differ from each other? Now, the difference between the actual observation point and the predicted one, so remember, if we didn't know how long it would take to drill the additional 5 feet, but we were given a starting point, we would throw it into the linear regression line and we would get this output. We would have guesstimated that it would take this amount of time. But if we actually went out into the field and did the experiment, they're saying that this is how long it would take. So the difference is an error, and this is unexplained deviation. So it means that the depth in which we start does not help to explain the difference between the prediction and the actual outcome. Now, the difference between the predictor value and the average is explained by the starting depth, and that would be the explained deviation. And then together, the explained plus the unexplained creates a total deviation from the average to the actual data point. And here's the formula, which you don't really need to do out by hand, because we have software that does everything for us. And here are some more formulas for if you were going to do this stuff out by hand. um, the unexplained plus the explained is always going to be equal to 1. And your coefficient of determination is the proportion of the explained variation over the total, which is also equivalent to 1 minus the unexplained over the total. Let's take a look at an example for determining the coefficient of determination. And let's find and interpret that. So remember, we already knew what the correlation coefficient was, 0.773. We just simply square that value to get the coefficient of determination. And then we make it a percent in order to interpret. So what this number says is that 59.75% of the variability in the drilling time is explained by the least squares regression line. So it's telling you how good of a predictor the prediction line is. So approximately 60% is explained by the prediction line, and 40% of the variation is not explained with the prediction line. If we take a look at these three data sets, and for this particular example, what this data is telling us is really unimportant. I just want to show you what the graphs would look like for different coefficients of determinations. So in these little graphs, you can see that data set A, all of your observed values happen to pretty much fall on the predicted values. And therefore, you would be looking for a very high coefficient of determination because you are saying that the variability, which there isn't a whole lot, is primarily explained by the prediction line. So you can see they all line up. Now it drops down when the points start to spread off the predictor line, and we drop really low when the points are very spread out. So again, the connection between the correlation coefficient and the coefficient of determination, they have a strong connection because you square one to get the other. And so if you have a very small, close to 0 correlation coefficient, then you would expect that the variation um, to be very low, that is explained by the prediction line because your error is so large. You predict this value, but really the value is over here. That is a huge error margin. Okay, performing residual analysis on a regression model. So residuals play an important role in determining the adequacy of the linear model. In fact, residuals can be used for the following purposes: to determine whether a linear model is appropriate to describe the relationship between the predictor and the response variables, to determine whether the variance of the residuals is constant, and to check for outliers. So if you're looking at a residual plot, which my next example in our guru, I will show you how to get that. You are looking for there to be no increasing or decreasing in the dots. They should just look like spray can, dots everywhere. But if you do see very clear increasing and decreasing portions of the residual plot, then you can conclude that a linear model is not appropriate for this data. Sorry, I have a bug flying in my face. So looking at this example, a chemist has 1,000-gram sample of radioactive material. She records the amount of radioactive material remaining in the sample every day for a week and obtains the following data. So here is the scatter plot of the data. It has a strong negative line here. So I'm not surprised when I see the correlation coefficient is very close to a -1 because it has a slight curve to it, but they're pretty lined up here. So if we drew the least squares regression line, we can see, okay, these dots are not falling very far. I would expect the coefficient of determination to be quite high. But when I look at the residual plot, I see that the linear model is not appropriate. So a linear regression actually is not appropriate for this data because the residuals is showing that there is increasing and decreasing, and therefore what we can't see with the naked eye, this residual plot is telling us that we should not be using a linear model. So if a plot of residuals against the explanatory variable shows the spread of the residuals increasing or decreasing as the explanatory variable increases, so essentially as you read left to right, then a strict requirement of a linear model is violated. This requirement is called constant error variance. which is referring to whether the error is constant or not, and therefore that's all about linear models. They're all about a constant slope. The statistical term for constant error variance is that word. Introduction to multiple regression. So now we're starting to talk about regression lines, but with multiple variables. In many cases, many data sets, it is not just one input and one output. It has several factors that contribute to the result of an output. So in this example, we are looking at essentially an initial point, an error, and all of your variables and their slopes. Okay? So to help us find all of those correlation coefficients or those slopes in the regression line, you can build what's called a correlation matrix to show the linear correlation between each pair of variables under consideration in a multiple regression model. So our data set we are going to use, and we will shortly switch over to our guru to show you how to do this in our guru, is a cheese data set. So as cheese ages, various chemical processes take place that determine the taste of the final product. The next two slides cover the variation between chemicals in 30 samples of mature cheddar cheese and a subject measure of taste for each sample. So you can see that we have a taste. I have no idea what scale these numbers are coming from when it comes to what does a taste of 20.9 mean. So when we're looking at data like this, typically when we are analyzing data, it comes with like what's called a dictionary. And in that explanation would be how the variables were collected, the units in which the variables are being used. In the case of taste, it would give us an explanation of what kind of scale they were using to determine this taste value and what it means. So we're seeing that we have three: the the three qualities: lactic, H2S, and the aesthetic, acidic. That word. And this data set I've already created into an Excel file for you. It is posted in our class folder. So here is the correlation coefficient, and how we read that. How we read that is that this variable has a moderate effect on taste. This variable, H2S, has a much higher, in fact, it has the highest effect on taste, and lactic has quite an effect on taste. And then you can take a look at the relationships between the inputs as well. So between this variable and this variable, you have your correlation coefficient and so on. Okay, so let's use technology to analyze this a bit further. So let me stop sharing PowerPoint and head back to our guru. One moment while I make our guru prominent on my screen. Here we go. Okay, so I'm back in here. You're going to want to import the multiple regression cheddar data that's in Blackboard. Remember to download it first and do the whole import data thing. So if I double click on it, I should be able to take a look. I'm going to close all these other tabs from the last example. Kind of lighten the load here on top. Okay. So I see that, okay, there is one heading where I have all of the titles of each column and the data. It looks pretty good to me. Great. Let's go to analytics. And under analysis, let's do linear regression. So I want to select my multiple regression cheddar data set. The response variable is the taste. Now we have to create a formula when you're doing multiple regression. Really, I just have to tell the system what variables am I using as the inputs. So that would be this variable. So we double click, plus double click, plus, double click. Okay, so now it tells me use these three in order to get taste. They all contribute. And let's select the eyeball. Okay, so in here, I can see the coefficient estimate. This is this is for the regression line. So you have 19.671 times the input of this variable plus 3.9 times the input of that variable plus 0.32 times the input of that variable minus the y-intercept will result in the taste value. Here we have our coefficient of determination, so that's 0.65. So we would interpret that to state that 65% of the variation between the prediction line and the observed value is explained by the predictors. Here's my residual plot. I can see that the dots are not increasing or decreasing, and therefore a linear model is sufficient. We will talk about the normal probability plot with residuals. That is coming up in future sections. Now, the one thing that this report didn't give me was the coefficient matrix. So that actually doesn't come up in the basic window. We have to go to details. We go to the very first line, model, estimates, and diagnostic graphs. And it is the data correlation. So you select data correlation and you put this arrow over and say, hey, I would like to see the coefficient matrix, an eyeball. So now I have this coefficient matrix, which we saw in the PowerPoint. The PowerPoint left off the duplicates and comparing, obviously it's a 1 when you're comparing H2S to H2S and so on. So they left out the duplicates. You really only need to look at this triangle here. But these are the important values which we saw also match in the PowerPoint. So again, if you're doing a project or an assignment, then you can save this right here in our Guru, but it's probably better if you download the file. I prefer that you don't upload a zip file into Blackboard because that's a pain in the butt. I have to download that and unzip it. So please do not upload zip files. Unzip it yourself and figure out which documents that are appropriate to be handing in if you're using this for as an assignment or one of the mini projects or case studies. Okay, let's head back to the PowerPoint. I think we have a slide or two left. Okay, so we took a look at the residual plot. Let's take a look. So again, here is the equation that I pointed out to you that came out in the report of our guru, the y-intercept, and then the slope for each one of the specific variables. We looked at the residual plot, which clearly did not show any increasing and decreasing. So we're good there. And look, they looked at the residual plot for each individual variable. We looked at the whole, but they also broke it up into all three variables residual plot, and all of them pass. And therefore, we see that we can use a linear model as appropriate for this particular data. So that concludes the rest of Chapter 9, 9.3, and 9.4 for this week.